Hi, everyone. I'm Mike Wong. I'm a NASA Sagan postdoctoral fellow working at Carnegie Science's Earth and Planets Laboratory, and I'll be giving the exoplanet overview for this primer on foundation models for astrobiology. So to introduce the topic of exoplanets, here is a video that shows all of the exoplanets that the Kepler Space Telescope has discovered, depicted as if they were orbiting a single star. So I show you this video not to hypnotize you into believing that exoplanet science is the coolest science out there, but just to impress upon you how many worlds we have discovered so far. Over 5,800 exoplanets have been confirmed to date. This is a staggering number, and it's going to keep astronomers, planetary scientists, and astrobiologists, and maybe even AI engineers up all night for many, many years to come to figure out if any of these worlds host biosignatures on them or signs of a global biosphere. So we are truly living in the age of exoplanets. Now, no exoplanet talk would be complete without a plot like this. What I'm showing you are those 5,000 plus exoplanets that we've confirmed to date, plotted on a graph where the x-axis is the period of that planet's orbit in units of Earth days. The y-axis is the mass of that exoplanet given in Jupiter masses. Every single point you see on this plot is one of those confirmed exoplanets, and the data points are colored by their detection technique. So you can see that most exoplanets discovered so far have been discovered either through the radial velocity technique or the transit technique. So the radial velocity technique is just when we infer the exoplanet's existence by the gravitational tug that it exerts on its host star. And the transit technique is when we notice the star's light dim periodically because the exoplanet has transited in front of it, as seen from our perspective on Earth. Now, there are a few important things to talk about whenever showing this plot. The first is that our exoplanet detection techniques are biased. They are biased toward detecting large, massive, closely orbiting planets, and they are biased against finding smaller, farther out planets. And so just because you don't see a lot of data points in the lower right-hand region of this graph doesn't mean those exoplanets aren't there. It just means we haven't found them yet. And one of the goals of exoplanet astrobiology, or exoplanet astronomy in general, is to push this boundary farther out in orbital period space and down in mass. So even though our survey so far is incomplete, we've still discovered a plethora of different kinds of worlds. Let me point out some of the major classes of exoplanets. So the first kind of exoplanets that were discovered are the so-called hot Jupiters. These are gas giant worlds that orbit super close to their host stars with periods of just a few days. So their temperatures are scorching in the thousands of Kelvin. And so the clouds that condense in these atmospheres aren't made of water vapor, but instead of things that would be gemstones here on Earth, titanium oxides, aluminum oxides, etc. We've also discovered a bunch of more widely orbiting, sort of classical or colder Jupiter-like planets, a population of planets that probably resemble to some degree the compositions of Uranus and Neptune. The most tightly orbiting rocky worlds are likely lava worlds whose surfaces are magma oceans and whose atmospheres are made up of vaporized rock stuff. And then, of course, we have our more traditional terrestrial planets, some of which may be suitable for life as we know it. And these are the ones that astrobiologists are most interested in. So what has the exoplanet revolution given us? Well, our observations have really expanded the diversity of planetary types and system architectures that we know exist in the cosmos. You know, who ordered hot Jupiters and lava worlds and the TRAPPIST-1 system with 7 Earth-sized planets lined up like peas in a pod? Now, these observations, in turn, revise our theoretical understanding of how planets form and evolve. We have to now explain how all of these wild worlds came to be. And then, of course, these theories then guide our future observations. What data do we need to go for next to help distinguish between our various models and narratives for planet formation and evolution? As a prime example of this, let me tell you about the Radius Valley that was discovered in 2017, or well, it was proposed actually before this theoretically, and then showed to really exist in this paper by B.J. Fulton in 2017. Basically, it is a bimodal distribution in small planet sizes. So on this graph, you have the x-axis being the planet size and Earth radii, and the y-axis is the number of planets per star that have been discovered in that size bin. So you can clearly see this bimodal distribution that points to two distinct populations, which we now call super Earths and mini Neptunes. And so this discovery needed some explaining and has spurred more detailed discussions of how planets gain and lose mass in their lifetimes. So this general picture that we now hold looks like this, that rocky planets first assemble these cores of dust and ice that then gravitationally are able to capture gas from the protoplanetary disk. After the gas disk dissipates in the first few million years of planet formation, those cores that were massive enough to accrete a lot of gas can hold on to it and become our mini Neptune population. But those slightly smaller planets won't be able to gravitationally hold on to that gas. Maybe it will be blown away by radiation from the young star, or perhaps the planet's own internal heat of formation drives the escape of the gas. But either way, we get this population of more rocky super Earths with much thinner envelopes of gas. One of the biggest questions in exoplanet science is, of course, whether or not any of these worlds host life. The habitable zone concept will guide our search for Earth-like planets and life beyond our solar system. Put succinctly, the habitable zone is the area around a star where liquid water might be stable on the surface of a terrestrial planet. If you're too close to the star, you might undergo a runaway greenhouse effect that boils away your liquid water, and then the water can get photolyzed and then escape into space. This, we think, happened on our sister planet Venus. If you're too far away from the star, your liquid water will eventually freeze into ice, as has happened on Mars. But if you're like Earth, our planet has produced stabilizing feedbacks that allowed for the emergence and evolution of life, although that life may be too dumb and wreck some of those stabilizing mechanisms. And we astrobiologists like the joke that the jury is still out about whether intelligent life exists in the universe, including here on Earth. So here's a more rigorous picture of the habitable zone concept. This is plotted with respect to the temperature of the star that those planets are orbiting. That's what you see on the y-axis. And then on the x-axis is the effective stellar flux that the planet receives, where 1 is the amount of flux that the Earth receives. And you see roughly a dozen or so potentially habitable planets that we know of. And also that there are various boundaries to the habitable zone because, and this is actually a very important point to emphasize, the habitable zone is actually just a hypothesis right now. It's a hypothesis built around the assumption that temperature is the 0th order control over whether or not life can exist on a planet. As an aside, you might question whether temperature is the real control over planetary habitability. And actually, some of Caleb Scharf's recent work has looked into the possibility that thermodynamic exergy or potential for information processing might be better metrics. But let's carry on with the temperature, the standard temperature story for now. Temperature is primarily governed by the amount of radiation that a planet receives from its host star and the spectral energy distribution of that radiation, as well as internal processes on the planet that affect that planet's climate. So habitability really is a planetary process that takes into account the context that planet is in terms of orbiting a certain type of star, and also the internal mechanisms of that planet that we need to model and understand if we want to truly make an assessment of any given planet's habitability. Now, how are we going to figure out if a planet is actually habitable? Well, the first clues are going to come from that planet's atmosphere. It's this thin layer of gas, after all, that makes life possible here on the surface of our planet. And here are just a few of the many reasons why an atmosphere is essential to promoting the flourishing of our biosphere. It provides essential nutrients that can get assimilated into the biosphere. It shields that biosphere from harmful radiation and regulates the surface temperature of our planet on many different spatial and temporal scales. And luckily for us, the atmosphere of an exoplanet is one of the easiest parts of an exoplanet to observe, thanks to the way that starlight interacts with the gases in that atmosphere. So certain wavelengths of light will be absorbed by the atmosphere, whereas others will be transmitted, and which get absorbed and transmitted or scattered depends on the molecular composition of that planet's atmosphere. And this allows us to make observations of exoplanets as it passes in front of its host star at different wavelengths. And depending on the wavelength of observation that you are looking at this exoplanet, it will appear different sizes. And so in this graphic here, you see that when you observe this particular planet at 2.3 microns, it actually blocks a larger area of the star's disk. And this is a sign that that exoplanet has something in its atmosphere that absorbs specifically at 2.3 microns. So in practice, this is how the data look. This is a transmission spectrum of the exoplanet WASP-39b taken by the James Webb Space Telescope, or JWST. On the x-axis of this plot is the wavelength of light that that exoplanet was observed at. On the y-axis is the amount of light that that exoplanet blocked. And you see that that amount of light is pretty steady between 3 and 4 microns, but right around 4.3 microns, that exoplanet appears quite a bit larger. And this is the telltale signature of carbon dioxide in WASP-39b's atmosphere. Now, carbon dioxide is a really exciting gas, especially when it comes to biosignatures and habitability, because it's one of those gases that life both breathes in and breathes out here on Earth. But don't get too excited. WASP-39b is very unlike Earth. It's one of those hot Jupiters, unlikely to host life as we know it. And so one thing that we need to work toward as a community is trying to make this kind of observation for an Earth-like exoplanet. But we may not be able to do that quite so reliably with the tools and technologies we have today, not even with JWST. What we really need is a brand new telescope that is going to go after signs of habitability and life on Earth-sized planets. And this is a telescope concept called the Habitable Worlds Observatory that we hope to launch sometime maybe in the early 2040s, knock on all the wood. This is a concept that currently the astrobiology community is very busy trying to define the parameters for. In its most ideal case, the Habitable Worlds Observatory will likely have a 6 to 8 meter mirror, be equipped with a coronagraph to block the starlight so that we can directly image the light coming from an Earth-like exoplanet. The wavelength coverage will span probably between 100 and 2,500 nanometers, which takes us through the UV visible and into the near infrared. And it will be equipped with this massive sun shield to keep the instruments cool so that its own thermal energy doesn't interfere with the sensitive infrared measurements that it's trying to take of an exoplanet. So the Habitable Worlds Observatory's mission goal is to directly image and characterize roughly 25 potentially habitable worlds and search for signs of life on all of them. And the reason why we need to have such a wide wavelength coverage is so that we can get a full census of the molecules that might be in an Earth-like planet's atmosphere. And so oxygen and ozone absorb in the UV and the visible, and water vapor, carbon dioxide, and methane absorb in the infrared. So we really need to get this full spectrum from the UV through the visible and into the near infrared to understand the entire planetary context for any given Earth-like planet. Getting a spectrum like this for an exo-Earth would be the dream for an exoplanet astrobiologist. But right now, we can do something similar for, again, these larger, puffier, hotter worlds. So let's talk about the nuts and bolts of inferring atmospheric composition. At the heart of this is model comparison. So in this plot, we see some exoplanetary data, which you're very used to looking at by now. That's shown in the white crosses. And overlaid here in 3 different colors are 3 different model exoplanet atmospheres. The lime green model has water vapor in the atmosphere. The magenta model has water vapor and methane. And the blue model has water vapor, methane, and carbon dioxide. And because that last one seems to fit the data best, we might infer that this exoplanet atmosphere has all 3 of those chemical species in it. But there are so many different knobs that you can tweak in terms of atmospheric composition, and fitting data points by eye is not a super reliable process. So in modern exoplanet characterization, we run what's called Bayesian inference models, which seek to optimize the fit of spectral data and retrieve probability distributions for all kinds of atmospheric parameters, from gas abundances to pressure temperature profile of the atmosphere to cloud opacities. But these models are all still very model dependent. When you say that you have detected a certain gas in an exoplanet atmosphere, really what you've done is detected a preference for a model that includes that gas over a model that does not. Furthermore, all of these Bayesian inferences rely on or have baked into them vast uncertainties about chemical and physical properties, assumptions about the planetary environment, and modelers' choices, which may or may not be super arbitrary. And sometimes these retrieval algorithms will find a best fit model to the data that represents a completely unphysical atmosphere, or there will be tons and tons of degeneracies in terms of the actual optimal fit to the data. And because the parameter space for all of these different atmospheres is just so huge, these retrievals can be very, very slow to perform. So this presents an opportunity for AI. Several groups have recently leveraged artificial intelligence to speed up their atmospheric retrievals through what they call Bayesian neural networks. These make atmospheric retrievals much faster and also more accurate. So maybe one day we'll even have an AI algorithm that circumvents these standard retrieval methods and all of the assumptions baked into them. That might be something that we could explore as a group. What are some other opportunities at the crossroads of exoplanets and AI? Well, I've been really lucky to have been working with Anirudh Prabhu for the past 3.5 years over at Carnegie Science. And Anirudh is a data scientist by training, and just meshing with him has been so exciting. So a couple of projects that we're working on right now, one in collaboration with Vasu Gatne, who's a Virginia Tech undergrad, is about exoplanet prediction. And so what Vasu has done is developed an exoplanet prediction pipeline using a well-known machine learning tool called association analysis, which is at the heart of any recommender system that you might encounter on Amazon or Netflix or YouTube. Association analysis basically deciphers rules that govern the behavior of co-occurrences of items. So if you go to a grocery store and you buy milk and bread, you may be very likely to also pick up some cheese. Except here, our items of interest are not consumer products, but rather exoplanet types. So a rule about exoplanet co-occurrence might go like this. If you have a sub-Saturn and a terrestrial planet in your system, you might also be likely to find a mini Neptune. And so in Vasu's paper, which is currently in review, she's figured out what those association rules are for the known exoplanets. That's what you're looking at in the graph here. The blue symbols are different kinds of exoplanets, and the red circles are different rules that connect them. And with these rules, she's able to actually come up with really awesome predictions for as yet undiscovered exoplanets that astronomers might go and try to hunt for. Another area where we're leveraging the power of machine learning is in the data-driven discovery of exoplanet natural kinds. We have these populations that we call hot Jupiters, mini Neptunes, super Earths, but these are relatively arbitrary and honestly solar system-centric classifications. And they may not be the best way of understanding the diversity of exoplanetary groups out there. And so our students, Jose Perez Chavez and Matthew Landon, have been using machine learning to discover data-driven categories for different kinds of hot Jupiters using various techniques. And what we see is 4 to 5 different categories of hot Jupiters jump out at us, which could hint at different formation mechanisms for these planets, or at the very least, give us more rigorous definitions for differentiating, say, between a hot Jupiter and an ultra-hot Jupiter and a warm Jupiter. So what challenges await us at the intersection of AI, exoplanets, and is our lack of ground training labels for the data that we have. We only have one example of a planetary biosphere, and that's Earth. In other words, we don't know the full possibility space of living worlds. At the same time, we don't have an abiotic Earth as a baseline for comparison. So that means that we don't know the full possibility space for non-living worlds either. And so that's why I think that unsupervised learning, anomaly detection, and maybe also some foundation models could be the keys to really unlocking AI for exoplanet astrobiology. And so let me wrap up with a few take-home messages. First, exoplanet discoveries drive revisions to our theoretical understanding of planet formation and evolution. We have to update our physical models for how planets come to exist based on the revolutionary knowledge that exoplanet surveys have given us. Many small rocky exoplanets are potentially habitable, but that's all that we really know at this time. We really have no idea if they are indeed habitable or have signs of life on them until future observatories give us better data. And so we're very much looking forward to the Habitable Worlds Observatory, as well as next generation ground-based telescopes that can get us that kind of data. Spectroscopic characterization of terrestrial exoplanet atmospheres is the next frontier in exoplanet astrobiology. And atmospheric composition will be our first clue about habitability and inhabitants. And then I think that there are many opportunities for AI to revolutionize exoplanetary science. I've mentioned a few here, but I'm sure collectively we'll be able to dream up many more. Thank you very much.